6 million years ago, the Earth stood on the precipice of a monumental shift. Deep within the heart of Africa, a single evolutionary lineage split. One branch remained in the safety of the dwindling forests, evolving into modern-day chimpanzees and bonobos. The other branch did something radical. They stepped out of the shadows of the trees and onto the open sun-drenched savanna. These were our earliest ancestors, the hominins. For millions of years, primates had relied on thick coats of body hair. Fur was an evolutionary masterpiece. It provided insulation against the cold night air, protected delicate skin from UV radiation, offered camouflage from predators, and served as a vital communication tool through bristling and social grooming. Yet today, Homo sapiens stand unique among more than 500 primate species. We are the naked ape. But why would evolution strip away a protective blanket that had served our lineage so well for tens of millions of years? To understand this mystery, we must first look at the profound consequences of standing up. As the climate shifted and Africa's great forests began to dry up, our ancestors faced a choice: adapt or perish. Food was no longer readily available in the canopy. It was scattered across vast open distances. To survive, early hominins began to walk on two legs. Bipedalism was a game changer. It freed our hands to carry tools, offspring, and food. It allowed us to see over the tall savanna grasses to spot predators. But standing upright came with a hidden, brutal cost: extreme thermal stress. Imagine the tropical savanna. The equator sun beats down with unforgiving intensity. Quadrupedal animals walking on all fours expose their entire backs to the direct overhead sunlight. By standing vertically, early humans significantly reduced the surface area of their bodies directly exposed to the noonday sun. However, they were now moving constantly across hot, open ground, searching for food. Walking on two legs is energetically efficient over long distances, but it still generates an immense amount of internal metabolic heat. When an animal's body temperature rises too high, its internal organs, particularly the brain, are at risk of catastrophic failure. Hyperthermia is a lethal threat on the savanna. Most mammals solve this problem by panting or resting during the hottest parts of the day. Lions, cheetahs, and baboons retreat to the shade when the sun is at its peak. But our ancestors could not afford to sit still. They needed to forage, and later to hunt. They were entering a niche that no other predator occupied, the daytime savanna. To survive in this fiery crucible, the early hominin body had to undergo a radical transformation. It had to become a master of heat dissipation, and the most formidable barrier to shedding heat was the very thing that had protected them for eons: their thick, insulating fur. Fur works by trapping a layer of air next to the skin, creating a barrier that prevents heat from escaping. In a chilly forest, this is life-saving. In a baking savanna, it is a death sentence. If early humans were to remain active during the day, that insulating barrier had to go. This transition did not happen overnight. It was a slow, agonizing process, spanning hundreds of thousands of years. As the necessity for long-distance travel increased, the evolutionary pressure to shed fur intensified. The stage was set for one of the most drastic anatomical overhauls in mammalian history. Our ancestors were about to trade their fur coats for a revolutionary new climate control system. Part 2. The Radiator Theory and the Mechanism of Sweat. To truly comprehend how humans lost their hair, we must look closely at our skin. It is a common misconception that humans have significantly fewer hair follicles than chimpanzees. In fact, a human being has roughly the same density of hair follicles on their body as a chimp of comparable size. The fundamental difference lies not in the number of hairs, but in their type. While chimps possess thick, pigmented, coarse terminal hairs, most human body hair has evolved into vellus hair, the extremely fine, pale, almost invisible peach fuzz that covers our limbs and torsos. But dropping the thick fur was only half the battle. If you remove an animal's fur without replacing its cooling mechanism, the bare skin is simply exposed to direct solar radiation, cooking it even faster. The loss of body hair could only happen in tandem with the development of nature's most sophisticated cooling system, eccrine sweating. Mammals possess two primary types of sweat glands, apocrine and eccrine. Apocrine glands are typically found in hair follicles. They secrete a thick, oily, musky fluid that is primarily used for chemical communication, scent marking, and warning signals. When you see a dog or a cat sweat through their paws, or a horse lathering up after a race, you are seeing a system heavily reliant on apocrine secretions mixed with fur. Humans, however, pulled off an evolutionary coup. We drastically increased our density of eccrine sweat glands. We have between 2 to 5 million of these glands distributed across almost every square inch of our bodies. Unlike apocrine sweat, eccrine sweat is almost entirely water with a tiny amount of salt. This is the radiator theory in action. When water evaporates from a surface, it absorbs thermal energy from that surface. This is latent heat of vaporization. If a creature is covered in thick fur, sweat gets trapped in the hair matrix. It evaporates off the tips of the hairs, cooling the air around the animal rather than cooling the skin itself. It is incredibly inefficient. But on bare, hairless skin, eccrine sweat evaporates directly off the epidermis. The blood vessels just beneath the skin are instantly cooled, and as that cooled blood circulates back into the body's core, it lowers the overall internal temperature. This gave early humans a biological superpower. We became walking evaporative refrigerators. This cooling system allowed our ancestors to unlock a completely new survival strategy: persistence hunting. Homo erectus, appearing roughly 1.8 million years ago, was built for long-distance running. They could pursue a kudu or an antelope during the absolute hottest hours of the day. The prey animal, covered in fur and unable to sweat efficiently, would rely on panting. But an animal cannot pant effectively while running at full speed. Eventually, the prey's core temperature would reach critical levels, causing it to collapse from heat stroke. The naked, sweating human, despite being slower in a sprint, would simply jog up to the exhausted animal and secure a high-protein meal. Shedding our hair and ramping up our sweat production transformed us from vulnerable foragers into the most relentless endurance predators on the planet. However, losing our protective fur coat left our bare skin completely defenseless against another lethal threat: the deadly UV radiation of the African sun. Part 3. The Melanin Trade-off: Genetics, Parasites, and Skin Pigmentation. When our ancestors cast off their fur, they exposed their bare, pale skin directly to the intense ultraviolet radiation of the equatorial sun. This presented a massive evolutionary crisis. Chimpanzees underneath their dark fur actually have pale, pinkish-white skin. It is highly likely that our earliest hairless ancestors also possessed light skin. But without fur to shield them, light skin under an equatorial sun is a liability. It burns, blisters, becomes prone to deadly skin cancers, and most importantly, UV light destroys folate, a crucial B vitamin necessary for DNA synthesis, cell division, and healthy reproductive development. Evolution's answer to this crisis was the rapid deployment of a natural sunscreen, melanin. Skin pigmentation became the vital armor for the newly naked human. Genes mutated to ensure that human skin became highly melanized, turning dark brown or black. This melanin absorbed and deflected harmful UV rays, protecting the vital nutrients circulating in the blood. Genetic clock mapping suggests that this intense selection for dark, hairless skin occurred roughly 1.2 to 1.5 million years ago. But thermoregulation and UV protection might not be the only reasons we lost our hair. There is another powerful complementary theory that explains our nakedness: the ectoparasite hypothesis. Thick fur is a paradise for parasites. Ticks, lice, fleas, and mites love nothing more than a dense, warm forest of hair to hide, breed, and feed in. These ectoparasites do not just cause irritating itches, they are vectors for deadly diseases. Typhus, plague, and various hemorrhagic fevers could easily devastate an entire clan of early hominins. By shedding our body hair, our ancestors effectively demolished the habitat of these dangerous pests. A hairless body made it incredibly easy to spot and pick off ticks and lice before they could transmit disease. Furthermore, as humans began to sleep in permanent home bases, caves, or shared nests on the ground rather than shifting tree nests every night, the parasite problem would have skyrocketed. Furless skin became a badge of health and cleanliness. This brings us to the realm of sexual selection. In the evolutionary dating market, health is everything. A mate covered in sores from ticks and fleas is an unhealthy mate. A mate with smooth, unblemished, hairless skin signals to the world, "Look at me. I have no parasites. My immune system is strong. My genetics are flawless." Over generations, this preference became hardwired. Humans began to actively choose partners who displayed less body hair, accelerating the evolutionary trajectory toward nakedness. Our hairlessness was a beautiful, complex tapestry woven from the needs of climate control, defense against microscopic enemies, and the profound driving force of sexual attraction. Yet, as we look at ourselves today, a striking contradiction remains. If we lost our fur to stay cool, why did we keep the hair on our heads, our underarms, and our pubic regions? Part 4. The paradox of what remained humans are naked. Yes, but we are selectively naked. The retention of hair on specific parts of our bodies provides the final compelling proof for why we lost the rest of it. Consider the hair on your head. If our ancestors lost their body hair to stay cool under the blistering sun, why on earth did they keep a thick, growing mop of hair right on top of their skulls? The answer is beautifully logical. When standing upright on the savanna, the top of the head is the only part of the body that remains permanently exposed to the vertical noon sun. The brain is the most heat-sensitive organ in the body. If the brain overheats, it is fatal. Thick, curly, or tightly coiled head hair acts as a literal barrier, a built-in sun hat. It absorbs the solar heat and radiation, keeping it away from the scalp, while allowing sweat to evaporate underneath it, keeping the brain cool. Our other remaining patches of hair serve equally vital, specialized functions. Eyebrows act as biological gutters, channeling sweat away from our eyes so our vision remains unobstructed during a high-stakes hunt. Eyelashes protect our eyes from dust and debris blowing across the plains. Meanwhile, the hair under our arms and in our pubic regions serves as friction reducers, preventing painful chafing during long-distance walking and running. Additionally, these areas are rich in apocrine glands, retaining chemical scents, pheromones that played an ancient role in human reproductive signaling. But as humans perfected this naked, sweaty, savanna-adapted body, a new challenge arose. Roughly 70,000 to 100,000 years ago, Homo sapiens began to migrate out of the warm cradle of Africa and into the colder climates of Eurasia. Having spent millions of years shedding our natural fur coats to stay cool, we suddenly found ourselves in freezing landscapes where hypothermia was the new enemy. But evolution is slow, and Ice Age winters were fast. We could not simply regrow our biological fur. Instead, we used our massive, highly evolved brains to solve the problem culturally. We invented clothing. We took the furs of the very animals we hunted and draped them over our naked skin. We became the only animal on Earth that wears the skin of other creatures to survive. In an ironic evolutionary twist, the loss of our biological hair forced us to develop the cognitive capacity, tool-making skills, and social cooperation necessary to create artificial insulation. Remarkably, science can track exactly when we started wearing clothes by looking at the evolution of lice. Genetic studies of lice show that the human head louse and the body louse, which lives exclusively in the seams of clothing, diverged from a common ancestor roughly 80,000 to 100,000 years ago. This genetic timestamp matches perfectly with the period humans began routinely covering their naked bodies. The loss of our body hair was not a random cosmological accident. It was the physical manifestation of our journey to becoming human. It is etched into our DNA, written in our sweat glands, and told through the story of our skin. Losing our hair forced us to develop dark skin for protection. It allowed us to hunt when no other predator could, fueling our growing brains with nutrition. It shaped our social bonds, altered our ideas of beauty, and ultimately drove us to invent clothing, technology, and culture to conquer the globe. We are a species defined by what we lack. We survived not because we were the strongest, the fiercest, or the most heavily furred, but because we were adaptable. Stripped of our animal coat, we were forced to rely on our minds. In the end, losing our fur was the catalyst that allowed us to inherit the earth.